that have joined us. Hello, hello. So it looks like you're having a Zoom party there. A few in the lab, I assume. Yep. And we've got Nate here as well. That's great. You could say hello, Nate, if you like.
Hello.
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 Yeah, we're Professor Burke's helpers.
Right. Okay.
Should we talk about our stuff or
We could. Yeah.
Yeah,
okay.
because we haven't started officially yet, so you guys are welcome to. That's the UAV Forge team.
Right. Okay.
Yeah.
You're
Let's
really
bring
nice to meet you.
Plenty
And I
longer.
see an aircraft with wings in the background. That's what I like to see.
Let's untether it. Let's just put it on battery.
Oh, you want to bring our plane? So this is our Let's get our wing. Planetary Stallion VTOL.
Yep.
We
Okay. Nice.
one of our team
So
members.
tricopter tilt quad plane. Nice. Yep.
It might be a little. It might be not what we want to actually implement our VTOL on. We might want to do a four plus flying.
Right. Okay. Yeah, an SLT. Yeah, I mean, there's advantages, disadvantages of different ones. I'm quite keen on the ones with more than one tilting motor, just because you can lose any motor and keep flying, and lose a servo and keep flying, which is very nice. I've got a very nice couple of race vehicles that are really good for reliable flight over long distances. And it was we were pleased that the control algorithms just came out in the wash for losing a motor and keeping flying. So it's because normally a quad, four rotor VTOL, if you lose one rotor, you're gone. But with tilting, if two of the rotors are tilting, it just will automatically compensate and keep flying with one motor out. Even in both in forward flight and in VTOL, so it can actually keep going on the mission, which is very nice. But no, the tilt try ones are nice and simple, so they're good, and can be a little bit tricky, the tuning sometimes on those, but they can work well.
Cool. What would you recommend us doing like for tuning something like that? Right now we're using the SATL plus Gazebo to do like physics testing, but I know you were using real flight earlier. Do you have any like
Yeah.
recommendation?
So look, creating a simulator and then tuning in the simulator, that can work okay if you pay a lot of attention to the accuracy of the simulation, particularly about things like moments of inertia, the mass distribution, the angles, the speed of actuators, that sort of thing. It tends to work better for fixed wing flight than for VTOL, just because none of the simulators really properly simulate things like vibration and frame flex. And that usually is the limiting factor in your tune for these types of vehicles, because they start twisting the vehicles and the vibration coming through it. And so the simulators are too perfect. So the first thing I'd start with pretty much any quad plane is a quick tune. You've probably seen the quick tune capabilities. So that used to be just a Lewis script. It's now available in the latest releases as in the C++ code, which means you can run it on lower end flight controllers like F405s. And quick tune is basically an automated version of a manual rate tune. I could show you guys how quick tune works if you're curious. So you could ask me about it during the main talk and I could demonstrate a quick tune. But so we start off with sort of a quick tune and then move on to doing some manual tuning, but with you can do a thing called a GCS PID mask, which allows you to stream the raw PID. You familiar with what a PID is? You heard of PIDs? Yep, you can stream the raw PID data to your ground station and then do some sort of manual tweaking on the tune. But before you get to that stage, you should also be looking at things like RPM feedback from your motors, get your filtering right, because there's no point doing a tune unless you're doing all of the filtering. You've got all the thrust linearization stuff done. Are you guys familiar with what thrust linearization is?
No.
Okay, well, that's one you should definitely ask about. So I don't have a set of slides for this talk, so I'm relying on you guys to ask me interesting questions. So there's one to ask about, thrust linearization. And that's very, very important that you get that as close as you can. And the harmonic notch filtering, definitely worth getting that right. Get all the angles right. Things like the parameters for that tilt try, for what the deflections are of the servos, so that it knows the physics of, when it's fully deflected up, it's at this angle, how much back angle it has, 20 degrees back angle, because in order to be able to fly backwards, the front motors have to tilt past the vertical back like 20 degrees or whatever, and all of those are important. So simulation can be a lot of fun, but if you do want to use it for tuning, it takes quite a bit of effort to get a simulator that's accurate enough for tuning. So quite often we use real flight, but it takes a fair bit of effort. The gazebo, again, quite a lot of effort to get it accurate enough that it's useful for tuning. But yeah, generally you can, as long as the thing is, operating correctly, you can just, get the thrust linearization, all the basics, and then jump into a quick tune and see how that goes. And that'll get you your basic rate tune, and then you might start playing with the angle P gains to make it a bit more responsive if you want that. Yeah, okay. All right, so we're actually a few minutes past. Peter, when should we start up?
Probably you could go ahead and start. It looks like there's still some streaming in.
All right.
So everybody, this is Andrew Tridgedal. He's the lead developer of ArduPilot, the drones that we've all been flying this quarter. And he really wants to interact with you, so please ask questions. You don't have to wait till the end. And we have, he's going to do about an hour, but if you students and he wants to stay longer, that's fine. And I'm really happy that he comes to give this talk. Thank you so much for giving your precious time to us.
Oh, you're very welcome, Peter. So a small correction, I'm what's called the systems lead for ArduPilot. So I'm the lead for the low-level stuff like operating systems, the RTOS, all of that sort of thing. Up until recently, I was also the lead for fixed wing and VTOL plane, but I've managed to hand that off to Pete Hall in the UK just recently, which is great. And I'm the leader of a few other bits and things like drone can and that sort of thing. But we don't have a single lead for the project. So we have a team of people. And one of the things we might talk about a bit is how you guys might join the team and get involved in development, and how, how the project works.
Can I start a question? So,
yeah,
like I said, they're all experienced with one student, one file of code, one drone. And you are living in a world with millions of drones and millions of lines of code and many, many, many developers all around the world. So it would also be interesting to explain to them and to me in the trenches how the real world actually works, because you
sure.
experience.
Yeah. So ArduPilot's used for a vast range of things. Student projects like yours, a lot of students use ArduPilot. A lot of just hobbyists and people who fly for fun. A lot of companies use it as part of their product lines. So a lot of commercial drones run ArduPilot. And so extremely widely used in lots of different applications. We've got a little web page on, types of vehicles that ArduPilot runs on, and, it's a huge range, submarines, boats, sailing boats, power boats, copters, helicopters, quad planes, or also known as VTOL fixed wings, balloons, blimps, and we've got one satellite, but it's just going ping. It's not very interesting. So all sorts of different types of vehicles that it runs on. And we have a dev team distributed all over the world. We've got, I don't know, 50 or 60 people in the dev team. So those, we have 2 meetings a week, which are open to anyone to join. The meetings are held on Discord. So just search for ArduPilot Discord to get our link into our Discord server. And then there's a weekly dev call channel in there. And anyone is welcome to join that. So if you want to come and listen in to the development process, then come and, it's mostly about discussing the latest pull requests on GitHub, where people are proposing changes and we do sort of real-time code review. So feel free to come and join in those developer sessions. And then we have, monthly partners meetings. We've got the whole concept of ArduPilot partners, which are companies that partner with us, on development. And we have an annual conference, and the upcoming annual conference in 2026 is going to be in Ottawa in Canada. And the organizer of that conference has joined us on this call. So Nate, do you want to say hello briefly? And there you go, Nate, you got your camera and things. Anyway, Nate is there. He's listening in. So he's the organizer of the Ottawa conference. So, if you want to come along to the Ottawa conference, you could try and get involved in development and see how you go. So,
hey, everyone.
So
you're welcome to come to the conference if you'd like. Be very happy to have you come up to Ottawa. So yeah, good luck with the talk, Tridge. I'm just working on some stuff this evening, so
sure,
I'm
no worries.
While working.
Thanks for joining in, Nate.
No worries.
All right. So I thought what I might do is Peter's handed me a couple of log files from you guys from your project over the last couple of months. And what I thought I might do is share my screen and have a bit of a look at those log files. And what I'm going to do is use that as a lead in to looking at the internals of ArduPilot and looking at how the different, subsystems of ArduPilot work. Now, the way I like to give talks is that the more interruptions, the better. So if you guys, unmute and ask a question or raise hand or whatever, I won't be out because I'm sharing my screen. I can't see you sort of waving at me. So feel free to just unmute and say hello. Or you can message Peter and ask a question, whatever you like. So can you guys all see my screen there?
Yes.
Great. Okay. So what I'm going to do is I'm going to start with, I'll just put away some of these bits that are going to come later in the call. And so I'll actually kill off the drone cam GUI tool. We'll get to that in a minute. Kill off that. And I've just got a couple of little logs here, and I'm going to pick this log. That one there, you guys might recognize that log with a great long file name. So I'm bringing it up in Mav Explorer. There's lots of different log analysis tools for ArduPilot. You've probably used the one in Mission Planner. I'm the developer and maintainer of this one called Mav Explorer. I don't run Windows usually. I can run Windows. I've got a Windows box over here that will be connecting to a bit later. But this is that log that you guys submitted. And what I was going to do is have a bit of a peek at this log and use that as a lead in to some tips around tuning and how some of the internals work in ArduPilot. All right, so what you guys did in this flight, you did a little autonomous mission. I'll just put away this window here. And all right, and I'll kill off this Discord so I don't get as many interruptions there. So, the basics you sort of see is sort of roll and pitch, where you see it here, it's in an auto mission and it's got, a desired roll and pitch versus achieved roll and pitch. And that's sort of the basic level of what it's achieving in terms of its attitude. What I'm going to do is, so ArduPilot, its control system for quadcopters is based, or multi-rotors in general, is based on what's called a nested PID system. So there's a whole bunch of different PIDs running all the way down from sort of the rate PIDs at the bottom, which is the angular rates in 3 axes and vertical acceleration. So 4 axes of control. Above that, you have the angular control. So this is what we're showing here, how it's doing at the angular control level. Above the angular control, you have the velocity control. And above the velocity control, you have the position control. And above that, you have the navigation controller. So there's a whole bunch of layers in the control of a multi-rotor in ArduPilot. And all of those layers are logged. And so what I'm going to do is, first of all, jump down to a lower level where I'm going to look at something called the rate outputs, right? Because the way ArduPilot controls any VTOL or any multi-rotor is that the high-level logic of the control breaks things down into 4 axes. It's the roll rate, pitch rate, yaw rate, and thrust. Thrust in body frame along the vertical axis in body frame. So then there's something called the mixer that takes those 4 axes and turns them into actuator outputs. For example, the values going to the ESCs to try to turn the motor at to produce a particular thrust. So we're going to look up at the pre-mixer level, and then we'll have a bit of a look at some of the mixer parameters, which involve something called thrust linearization, and then the actual mixer itself, and see how that works. So if we look up in this log here of this flight, one of the flights that you guys did, then we can see the roll output, pitch output, yaw output, and thrust output. Let's concentrate on something like the roll output. And we have a look in here, and we can see we've got a graph where we've got 2 axes of the graph. On the right-hand side, we're showing the attitude. On the left-hand axis here, we're showing the rate. So the rate here is in degrees per second. So you can see that the overall attitude wasn't bad, but it is a little bit noisy. You see the attitude jumping about a little bit, right? So when this was hovering, you would have seen the copter twitching a fair bit. It wasn't silky smooth. It was sort of twitching around. It was generally following the desired attitude, but it was doing it in this sort of noisy fashion. So if we look in that section there and we look at what's happening in the rate outputs, that's this red and green. The red and the green shows that it's quite messy, right? And where do you think it gets this rate.r values? Anyone, in this talk today, I'm expecting that you guys will actually have to think and answer questions. So where does it get that rate.r from? Any guesses? All right. Is their microphone's not working, or
like your IMU, your accelerometer?
Yeah.
Are these desired or measured? These are measured.
So the R is the measured, and in fact, yes, it is indeed. So if I show what devices are on this this particular vehicle, you see this vehicle has got a barometer, and you can see the type of barometer. It's an SPL06. It's got a compass, a QMC 5883L, and then it's got an ICM 42688 IMU, which provides 2 sensors. One is the accelerometer, and one is the gyro. And so this rate.r is just the x-axis of the gyro. And you can see it's quite noisy, right? It's a bit all over the place. Now, where is that noise coming from? Why is that noisy, and why does it matter?
Vibration.
Yep. Yeah, and where's the vibration coming from? Do you think it's vibrating like this when it's sitting disarmed on the ground?
No, it's probably coming from your props, your motor's spinning.
Indeed, yes. Okay, let's be more specific. So propellers, where do you think it comes from with the propellers? What's significant about the propellers?
It might not be perfectly balanced.
Yeah, it could be imbalance of the propellers, right? That's quite possible, but it might not be that, actually. Let me grab a vehicle here. It's a slightly different vehicle, but it's got the propellers on it, whereas the other quadcopter I've got here doesn't have any props. I'll just stop screen share briefly. And can you see my my screen with this sort of vehicle here? This is a quadcopter with wings, right? It's got no ailerons or anything, so it's got no surfaces. It's basically just a quadcopter with a bunch of wings on it, which means it can go to forward flight, but without any control surfaces at all. It's only got the 4 actuators. Right, so if we have a look at this propeller here, okay, what does the propeller do when it's spinning?
Produce lift.
No, what does it do? First of all, more low level than that.
Spin.
It spins. Well, I mean, we're in the air here, right? You can't see it, but it's got some air. So what's it doing to that air?
Displacing the air.
Accelerating.
It's displacing it. So it's pushing the air, drawing it in from the top, pushing it through downwards. What is that air going to hit on this vehicle when you push it down?
The turbulence.
The little arm that's holding up.
That's right, the arm. So when the blade is passing over the arm, you've got this high velocity air being shoved down onto this arm. What does that do to that arm?
Pushes it down.
Yeah, it sort of knocks it about a bit, right? So the frequency at which these blades pass the elements of the fuselage is called the blade passage frequency. And on most vehicles, that's actually the primary vibration you're getting, right? Now, notice this is a 2-bladed propeller, which means what frequency of vibration are you going to be getting from a 2-bladed propeller with an arm structure of a single arm? You're not going to get it out here because out here, there's no arm for it to the air to hit. Whereas this one, there is an arm, right? So what frequency is that going to be happening at? Double your RPM, indeed, because there's 2. If it was a 3-bladed propeller, it would be triple your RPM. And if you had a structure where the blades were going above multiple pieces of fuselage, you'd actually get hits on multiple of those, and you get other frequencies. Okay, so that's the primary source of vibration on this type of vehicle. There's also other ones. There's frame resonances, where the frame has a natural, the old wine glass thing, put your finger around the wine glass and there's a natural frequency that it vibrates at. Well, frames like this have natural frequencies as well. And so you tend to get a bit at the natural frequencies, the frame resonance frequencies. You get a bit from the motor itself spinning at the main RPM. You get all sorts of other little bits and pieces of noise, but typically the dominant one is what's called this blade passage frequency. All right, so let's go back and have a look again at your log. And so just put that one away and we'll share that one again. And one of you guys could hold up your vehicle if you like. We could have a look at what sort of blade passage, but it's probably got a single arm going back to the middle with like an X-frame quad. And so it'll probably have the 2 times RPM as your blade passage frequency giving vibration. So this noise is probably mostly caused by that blade passage frequency. Why does this matter? What's all this noise here? What's it doing to your tune? Any guesses? All right, well, just to save a bit of time. So most tunes on this type of vehicle are limited by one of 2 things. They're either noise limited or they're phase limited. And so your vehicles are probably noise limited at the moment. Basically, if you try and tune it too well, you end up incorporating too much of the noise. And the reason for that is there's this concept of control bandwidth. You guys met the concept of a control bandwidth of a vehicle?
I know a little bit. Yeah, like how it's kind of like you only have so much control, like possible, like for a particular, depending on the vehicle's like, characteristics.
It's about how quickly you are trying and the vehicle is capable of being controlled, right? So you might be controlling it really slowly, or you might be trying to get rid of all the little tiny twitches, which case you've got you're trying to achieve a higher control bandwidth. You're trying to push things faster. And as you raise the PIDs, what it's doing is it's trying to push the vehicle more rapidly, correct smaller and smaller time errors, right? Errors in smaller and smaller, increments of time. So down to sort of tens of milliseconds, even milliseconds type control. You've probably got control bandwidths of sort of 5, 10, 15 hertz of that sort of order at the moment of your vehicle. Quite low frequencies. Okay, so if you wanted to improve that, say you wanted to actually get rid of some of this noise in order to make the tune better. Because if you get rid of this red and green lines, this sort of noise here, then what that will do is that will, if we go back to where we were, looking at the flight here, you'll end up with less noise in the attitude control, and this little divots here in the blue line, which is your actual roll, measured roll, they will get less and less. And so you'll actually get a better tune. You can also physically isolate as well, but the problem with physical isolation is that adds a lag. It's sort of imagine if you mount it on a very, very soft mount. Well, you might, then your motors are trying to control that soft mount, but that soft mount is sort of slewing all over the place independently of the motors. In other words, the motors aren't directly controlling the attitude of the thing that's doing the measuring, which is the IMU. And so you end up with this sort of lag coming through depending on how soft the mount is. So what do you think you can do to get rid of some of this noise?
Filtering.
You could do filtering, right? And you have done some filtering, I'm sure. If I have a look at what filtering, you've got a gyro filter of 91 hertz. Okay, so you've got 91 hertz. So now that is like a two-pole. I think it's a two-pole Butterworth filter we've got there, and so it's not a really sharp roll off. It doesn't mean that above 91 it just cuts it off, and below 91 it passes through. It's sort of a slow roll off, right? So that's the point at which at 91 hertz it will have attenuated by that's probably the 70% attenuation at 91 hertz. Now we can look. There's another type of filtering we can do called harmonic notch filtering. Now, have you guys met harmonic notch filtering?
To some extent, yes.
All right, so it's turned off on your logs. Let's have a look at how you're controlling these ESCs. So I see that this particular vehicle is using D-Shot 600. All right, well, that's great. Have you ever heard of something called BD shot?
Yeah.
Yep, bidirectional D-Shot. Yep.
We don't have our ESCs are really low cost.
Mm-hmm.
That's why it's not bidirectional. So
yeah, a lot of the low cost ones can actually do bidirectional. Depends on, do you know which model it is?
Well, it's an 8-bit, which you're going to laugh at.
Right.
So
okay.
I
no.
thought,
Some of the 8-bits can do BD shot as well.
Oh, really? Okay.
Oh, yeah, definitely. I personally, I work on AM32, which is a 32-bit one, and you can get very cheap AM32 ESCs. But a lot of the 8-bit ones can do BD shot. So if you did BD shot, you would be able to get RPM feedback. And so it means that each time it sends this D-shot packet out to the motor, or to the ESC responds with a packet giving the RPM. And you can do a more advanced version of BD shot, which when every nth reply, it also gives things like temperature and voltage and that sort of thing, which means you can get actually full telemetry stream back from the ESC into the flight controller, giving you a lot more information. All right, so what could you do with that if you had RPM feedback from each of those motors?
You would know what frequency your noise is at, and
Yep.
filter it better.
Yes, indeed. Yes, you would know what frequency the filter is at, and sorry, the ESC is running at, and you could create what's called a notch filter. So instead of a low pass filter, you create a filter that has a little notch. It's not a perfect square like that. It's more like a wide sort of thing like that. And it would enable you to, remove the noise around the frequencies of each of the individual motors. Now, you can also do this even without RPM feedback, right? So you could have on your log, on your vehicles, you could have set up something called the throttle-based filter, notch filter. And what that does is that estimates the RPM of your motors based upon the current throttle level. And you can do that either as an overall throttle level, or you can do it as a per motor estimated throttle level. And that would get rid of a lot more noise, even without having the RPM feedback from your ESCs. So what I'm going to jump into is I'll just do my video for a second to show you a little vehicle that I'm going to be playing around with. So this is a little quadcopter called an Edu 450. You see that one there? And it doesn't have the props on it at the moment, so less interesting, but also means less likely to slice my finger off in my study. Now, it has got actually drone CAN ESCs, AM32 drone CAN ESCs, and this is because I'm developing the firmware support for these, but it's got RPM feedback, right? And so what I'm going to do is show you a log of this vehicle with the RPM feedback, but just noting that you can do a lot of what I'm going to show you even if you don't have RPM feedback, just using either the overall throttle-based filtering or using the per motor throttle-based filtering. You would have to get a log with the raw gyro logging, and your logs don't have that. So you would have to do a flight, a little hover for a couple of minutes with this raw gyro logging. There's a parameter, INS raw log opt, and you can also do batch logging. That's another option. And so this sort of logging logs the IMU data at a low enough level that it can run through this analysis tool. Right. And so this analysis tool is part of a set of tools called the ArduPilot Web Tools. And you see it firmware ardupilot.org/tools/web tools. Well worth exploring these tools. There's some fantastically useful tools in here. And the tool we're going to use here, this is the filter review tool. And what I'm going to do is bring up a log from a flight I did a while ago on this little vehicle that I just showed you. And what this analysis tool is doing is showing, red line of my altitude, the green line here, what my throttle was. It's not a great log for doing this analysis, actually. You really want a log where the throttle, the green line, is constant for 30 seconds or so. But I didn't find a log of that sort this morning when I was looking through for logs to show you. So we'll just have to go with this one. All right. And now what we can do is when we've got those extra logging bits on, it's able to log. It's got 3 gyros on this, so 3 IMUs. And we might discuss in a little while why you might have more than one IMU on a vehicle. It's only logging the primary gyro here. And what I'm going to do is just get it to display the x-axis, just for simplicity of this primary gyro. And this is now showing a FFT. So this is showing frequency on the x-axis and amplitude on the y-axis. And can you see these couple of peaks here, right? There's a peak there around 102 hertz, another one about 204 hertz. Notice that's twice. So you get these harmonics, and then you got another one here at 313, then another one here, it goes up in these little harmonics, because you get the first blade passage frequency, but you also then get the harmonics of those frequencies, right? So you get multiples of those frequencies turning up. And so what we want to do, we can then design a filter for this vehicle, right? And this is the vehicle that the filter that I've already had on the vehicle, and I've told it that this filter is going to be fed by the ESC telemetry that this vehicle has. And you can then say how many of the harmonics you want in here. I've also got a fixed frequency one at 32 hertz here. That's for a frame resonance, because I noticed that there was a extra little peak down here around 32 hertz or so, and that seemed to be a frame resonance of this particular vehicle. So I'm shoving in an extra little narrow notch filter at that frequency, right? So I can now display those notches that I've got here on this graph, and I'll go back to the sort of the overall display, and it should go back. I don't want to, yeah, okay, just go back to auto scale. So then we can see these notches, and you can see that there's the little fixed notch at 32 hertz. These ones here, they're not quite perfectly aligned with that peak, but it's not terrible. And then there's another one here, and another one here, another one here, and that's reduced the noise considerably from what it would have had otherwise. And these peaks, these are in decibels, so it's a log scale on the vertical. So the difference here between minus 9.8 dB and minus 55 dB, that's huge. So by using notch filters, we cause a lot less phase lag. And so the phase lag really matters, because if you just use a low pass filter, basically that means it lags your signal at low frequencies. And that means that the flight controller doesn't see movement at the same frequency it's actually happening. So some of the low frequency information is lost using a low pass filter. And that means that it limits how tightly you can tune it. By using notch filters, we can get rid of the noise just at the frequencies that the motors actually generated. And so we can end up with a lot better tune. Now, there's a lot more to this. We can go down and have a look at this sort of spectrograph type thing where we can zoom in and see, you know, this sort of waterfall effect. We can look at the frequency responses, the phase lag that we're getting. There's lots of stuff we can do here. But I'll leave you guys to explore this tool at your leisure. And there's lots of videos and things on how to use this, but definitely worth doing. If you want a good tune, you definitely should look at that. Any questions about that before we move on to other things?
Yeah, I wanted to ask real quick. You mentioned you were using CAN ESCs, at least for your protocol. I was wondering, is that just like a feature? Is there a benefit to CAN over like PWM or BD shot?
Great. This is exactly what I wanted you to ask, because I'll now show you these little CAN ESCs. And so thank you very much. And we didn't even pre-plan this. So what I'm going to do, that little vehicle I just held up, right? So I'm connected to that vehicle somewhere here. There, I'm connected to it. And then I've got my console here. There's the vehicle there. And I'm going to connect using the MavCAN, DroneCAN over MavLink and go and have a look at these ESCs, right? So this is now using the DroneCAN GUI tool, and I can look at one of these ESCs, fetch all of the parameters of the ESC, and there's a lot of controllability you can tweak in the ESCs. Much easier to tweak the behavior of the ESCs, like things like advanced levels and cutoff limits and signal filtering and all sorts of things inside the ESC. We can also bring up a little thing to control the ESC. So here we have an ESC management panel, and I can now, if I move my microphone here, you can probably hear that motor starting up, right? And so it's currently running at 7,200 RPM. I'm getting the temperature, the current, and the voltage. And so all of that being fed across DroneCAN. If I bring up the overall bus monitor, I can look at what's coming across the DroneCAN, and I've got information on ESC status, which is what we were just showing, but I've also got information from things like my GPS, and, you know, the commands, etc. So it's a much more comprehensive protocol. So big, expensive vehicles tend to use DroneCAN, but AM32 drone can is much more accessible. You can buy drone can AM32 ESCs very cheaply. So definitely worth looking at those. There's Hoybean is one of the ArduPilot developers, and he's got a store where he sells these lovely little ESCs, and from a company called Vim Drones. Anyway, so yeah, a lot more information. It gives you all of those RPMs and things you can do filtering on, but it also gives you a lot easier level of control and upgrade. So I could upgrade the firmware just by pressing this upgrade firmware and then pointing it at a new firmware file. It'll upgrade the firmware on that ESC. Does that sort of be clear at all into how DroneCan is a nice way of controlling devices, not just ESCs, also servos and GPS and airspeed sensors and all sorts of bits and pieces you can do with DroneCan.
Yeah, absolutely.
Yeah.
And then adding on to that, just what software are you using for all of this, like all the debugging and all of this? Because this stuff looks really useful.
Yeah, so I'm connecting with, it's all open source stuff. I'm connecting with something called MavProxy, which is a ground station that myself and Peter Barker are the developers for. So it's a Python-based ground station. So it's just pure Python. It's got lots of capabilities. One of the nice things about MavProxy is it's sort of an engineering so engineering ground station, you have lots of graphs running up simultaneously. So you notice that I've got a graph of the RPMs here. So there's, RPMs coming from these ones simultaneous to my voltage, and I can graph, something else. What do I want to do? Board status, power status dot, the voltage from my board coming up as well. I'll just shut these motors down. They're quite noisy. So it's very much an engineer's ground station where, so you can have lots and lots of graphs simultaneously, lots of customization. It's a very different from an end user ground station like Mission Planner. But if you want to get into it at all, if you're into Python, then just look up MavProxy, all of the source codes there. You can build and run it yourself. Use that.
Yeah, we actually used MavProxy, but we weren't aware of all these tools within it. We kind of just used.
There's a lot of tools. The log analysis stuff I'm doing here is using something called Mav Explorer, and that comes as part of MavProxy. It's got a whole lot of canned graphs here where we might look at, EKF innovations and that sort of thing. And we might get into the EKF in a minute, maybe using some of your logs, the state estimation. And yes, it's got a lot of these sort of canned graphs and things where you can really dive deep. I've got a separate lecture that I gave a while ago on using Mav Explorer for log analysis. It's a couple of hour-long video, but it's up on my YouTube channel. So feel free to jump onto that and learn a lot more about how to use Mav Explorer for log analysis. But I might just briefly jump into one of your logs. And so this is one of the logs that you guys had. And we'll look at a little bit of the state estimation stuff. So because really, it's useless having a multi-rotor or any vehicle unless it's got good estimates for your state. And by state, principally, I mean your, attitude, roll rate, pitch rate, yaw rate, velocity, position, climb rate, all these types of things. It's ArduPilot's primary state estimator is called EKF3, and it's got 21 states that it estimates. So a lot of different states that it's estimating, even things like wind estimation and stuff like that. It's a neat trick. It can actually do wind estimation on a quadcopter using what's called drag fusion. So if we have a look here at your innovations for this flight log, and apologies to whoever's log this is that I'm picking on, it's just one that I've got available. So you see that these are what's called the normalized innovations, and normalized innovations are innovations that are scaled against the cutoff point where it starts rejecting that sensor. So the velocity innovations are principally coming from the GPS velocity, And you see that we're getting innovations up above 0.4, 0.5. And basically, if it got to 1, it would start rejecting the sensor. And so these are quite large innovations. We can also show the innovations in SI units. So let's have a look at your innovations. Let's have a look at that velocity innovation northeast and velocity innovation down so the three, so horizontal and vertical axes, because this vertical one is a 3D velocity innovation, and we can now get these in SI units. And so these are in meters per second. And you can see your horizontal velocity innovations are reasonably low. They're not as good as they could be. They're sitting at around sort of 0.2, sort of 0.4 meters per second peak to peak. But vertically, you're seeing velocity innovations of sort of, 1 meter per second. So you can imagine that if you had an error of 1 meter per second in your vertical velocity, that you're really not going to fly all that well, right? It's going to start drifting up and down. So you really want better velocity innovations. And some of that is going to be coming from noise, from motor noise affecting the accelerometer. And some of that is going to also be coming from things like, barrow effects, because my guess is that you're using the barometer. You are using barometer as your primary vertical source. What do you think happens when you're doing a takeoff and you put thrust down onto the ground, and that thrust hits the ground and causes a pressure buildup below the copter, and that pressure impacts the barometer, and that's your primary altitude source. So you end up that you're sort of mixing in a bit of, thrust to pressure noise or pressure offset on your barrow, and that's affecting the state estimator and not allowing it to get really good vertical velocity estimator. Although this is principally coming from the vertical velocity of your GPS. So if we have a look at your GPS VZ, and we look at XKF1 0.VD, if I could type correctly, then this is the GPS 0.VZ is the velocity down as read directly by your GPS, and the green line is the EKF, the extended Kalman filter's estimate of your vertical velocity. Now you see they don't match particularly well. There's significant differences between them, right? And so basically the EKF is overruling the GPS's vertical velocity. What type of GPS do you guys have on here? You've got it's an M10. All right, and let's have a look at that M10 and see how healthy it was. And so it was up to sort of 26, 27 satellites, so it had probably been powered on for a while. And let me see how long so it had been up for 400 seconds. So quite a while, sort of, what's that, 6 minutes or so, 6 or 7 minutes. And so the M10 is a bit notorious to being not very good in the vertical. It's a low power GPS. It's really aimed for sort of lower power applications. And so it does have a bit of error. But it's perfectly flyable, as you found. The EKF is correcting for it. So the EKF is essentially overruling the GPS's vertical velocity estimate using a combination of the other sensors, principally the IMU and the barometer. And so it's looking at the IMU and the barometer data and saying, well, no, that doesn't make sense, that GPS vertical velocity. We're going to overrule it and produce this smoother and hopefully more accurate value. But this is where having multiple IMUs is very nice, because you've got multiple IMUs and multiple GPSs and multiple compasses. You can compare them and see if they're consistent with each other. And that can really help in making things more, it's much better for log analysis, but also allows it to produce multiple state estimates for the different IMUs, and then it can switch to the state estimate with the lowest what's called the lowest innovation. So the innovation is the difference between the measurement and the prediction. So an EKF works by continuously predicting what the next measurement is going to be. So it predicts what your GPS is going to give for vertical velocity, and then it gets a reading from the GPS, and it compares the prediction and the reading, and the difference between the prediction and the reading is called the innovation. And the innovation is the best metric for how happy your EKF is and how consistent your sensors are. Because if all of your sensors are perfectly consistent, your innovation is going to be very, very close to zero. And then you've got a very happy EKF, and a happy EKF leads to a happy vehicle. All right. So how is that for the 5-minute tour of an EKF? Any questions about that at all? Noting we're already up to nearly 50 minutes in this, and we're only at the very beginning of the sort of stuff I wanted to get into. Any questions at all about EKFs and state estimation and that sort of thing?
I guess this is sort of regarding the multiple GNSS sort of receivers. Can RTK, like implementing like RTK systems, improve like the state estimation, I guess?
Yes, it does. Oh, yes, okay. Definitely. So RTK, there's lots of ways of improving. You can have dual frequency or multi-frequency GNSS systems, where it's not just having one frequency of signal coming from the satellite, that each satellite is actually outputting, all the satellites output lots of signals in different frequencies, but it means you have a receiver that can receive more than one frequency. That is the first thing to do in improving your GPS performance, because if you've got more than one frequency, then you can use the different frequencies of radio waves will propagate through the atmosphere at different velocities, right? They're not all going exactly the speed of light. They're slowed down. It's something called atmospheric dispersion, which slows down the signal as it's coming through the atmosphere. And a lot of the error in GPS is because of ionization in the atmosphere, where there's, high energy particles in the atmosphere causing, molecules to be ionized. That causes the signal to be lagged from the satellites by tiny amounts, tiny amounts, but enough to throw off your position estimate. Now, what you can do is if you've got two frequencies coming from your satellites down to your receiver, then it can use the difference in arrival time of those signals of those two frequencies to build a better estimate for the dispersion in the atmosphere. And that means it can build a better atmospheric model. So the little receiver is actually building a model of the atmosphere along the paths between the receiver and the satellite for each of the satellites that it's tracking. And those atmospheric models allow it to correct for the dispersion happening in the atmosphere due to the ionization of the atmosphere, and that allows it to get a much more accurate fix. So that's the first thing you do, and that will get you a much better fix. So if I actually did a blog post about this a few years back that's well worth, if you're interested in GPSs, you should definitely look at this blog post where I did some analysis without lots and lots of different GPSs. So this is, I had a table with, lots of GPSs on the table. And then I had it both out in an open area, no sky view. And then I also had it in my backyard under some trees. And then I did analysis of what's called the SEP and HEP, which is the accuracy. Now you guys I didn't have the M10 because the M10 wasn't available at this time, but your M10 is a bit worse than like a, probably it's around an M8 roughly. And you can see these are sort of the circular error probable. What this is saying is for this type of GPS, it's going to get a position accuracy that 50% of the time the positions are within 2.26 meters. And 99% of the time the positions were within 6.92 meters. If we use a dual frequency GPS, you can see these are dual frequency GPSs, and you can see the accuracy is vastly better. These are the height probabilities, so similar to horizontal, but for height. If we go down to RTK, if I turn on RTK and I look at the equivalent of your GPS, which is sort of like this one, it doesn't benefit from RTK at all. It can't do RTK. But if I look at the ones that are RTK capable, they're now, 50% of the time it's within 1 centimeter, 99% of the time it's within 3 centimeters. Now that's a big difference, right? So does RTK help? Yeah, oh yes. It also helps with the velocity, which is really, really important. Much better velocity tracking. And that helps the EKF a lot. So yeah, very, very clear. You could have a look at this. Just look for big GPS roundup and you should find my blog post about that. I've done some other blog posts about this type of thing in other cases.
So you would recommend L1, L2, L5 plus RTK?
Well, generally GPSs are either L1, L2 or they're L1, L5. L5 is still actually experimental, which means GPSs that implement L5 actually can receive it, but won't use it unless you set a special flag in it to say use experimental frequencies, because the L5 frequency is still marked as experimental. Triple band ones aren't really widely available yet. Certainly not at consumer prices. But dual band ones are much more expensive. For hobbyists, I wouldn't actually do that. You might be paying $400 or $500 for a dual band RTK capable GPS. They're lovely, but they're quite expensive. They'll cost you as much as all of the rest of the vehicle put together. But if you're doing a big expensive vehicle, anyone doing serious commercial stuff with ArduPilot would have dual band RTK capable, very likely RTK enabled GPSs. All right, I might jump into another thing here because I know we're running out of time, and I really wanted to show you a little bit about what you can do with looking at the internals of ArduPilot, right? Because I want to get you guys sort of interested in some of the internals. And so I'm connected with MavProxy to a vehicle here. And so this is actually that little Edu 450, the little one with the drone can ESCs that I showed you. And I can use the FTP command to poke around in the file system. And you'll notice if I look in the file system, it's got these extra little magic, what's called virtual file system layers. And if you want to learn the internals of ArduPilot, it's worth having a look inside these little internal bits and pieces inside ArduPilot. So what you'll notice, there's a whole lot of these. These are called virtual files inside. So they're implemented inside the flight controller. They don't exist on the microSD card on the vehicle. And I can go and fetch these, and we can look at and I need to go and get the file rather than list it. And so what I've got here is, I'll just make that so you can read all of it, hopefully. So what this is showing us is all of the threads of execution running on this. It's an H743 microcontroller. You guys had F405 microcontrollers on your flight controllers, which was a bit previous generation. H743 is a bit more powerful, but you still have, this. This is available to you guys if you want to look at it. And you can see all of the separate threads that are running ArduPilot. And one of the things about ArduPilot is we have this philosophy of a thread per bus. So you have a whole lot of buses in ArduPilot. So you have multiple I2C buses, multiple SPI buses. You have multiple UARTs. Each UART is its own bus. You have multiple CAN buses. So all of these buses are basically data transports, right? Lots of different data transports. And so we have a thread for each bus, which is processing the I/O, the input-output for that bus. Why do you think we have a thread per bus? Why do you think we chose that fundamental architecture for ArduPilot?
If you have like different frequencies or data transfer rates.
Yeah, the key reason is
modules you would want to connect. Oh, sorry.
Yeah, that's certainly true. You want multiple buses so you can connect lots of things together. But why do you have a thread for each one? So I should explain what a thread is. So a thread it's like a virtual CPU, right? So we can have a whole lot of threads, and they've only got the one CPU on this vehicle. Other ArduPilot vehicles have multiple CPUs. This has only got the one CPU, but that one CPU can be like time sliced to allow multiple threads of execution as though they're each, so you're simulating having lots of CPUs, each running a particular task, right? So we have what's called the main thread, which is the ArduCopter thread. That's the one that's running the high level navigation and attitude control and that sort of thing. Then we have, a UART receive thread. This is the USB thread. We have sort of timer threads, RC input and RC output threads for our RC control, networking threads. We have drone CAN threads, all the different SPI, which is your IMUs are connected on what's called an SPI bus, which is a very fast data bus for, the high rate for SPI. PPP is how it's doing networking. So this one's actually implementing TCP/IP. It's got a web server on this copter. You can actually log into it with a browser if you wanted to. So okay, so all of these threads, you can go and have a look at the priority of each of these threads, the stack pointer, how much stack it's using. You can have a look. If you turn on detail, there's a option when you're building to get more detail in this, giving you how much CPU each thread is using. Let me have a look at some of the other things in /sys. Let's have a look at, say, the tasks. And so I'm going to get sys task.text. Right, so these, if you've poked around in the ArduCopter source at all, right, you will notice that there is a big tasks table. So there's this tasks table of all of the things that the main thread needs to do. So we have the main thread, which uses most of the CPU, and within that main thread, we slice things up with something called the AP scheduler, which slices up the time it spends on each of these little subtasks. So these are these list of tasks, and these numbers here are how long it expects each task to take to run. So it's expecting the RC loop is taking not more than 250 microseconds, and how often we run it. Apologies, that's actually 250 hertz we're running it at. We're expecting it to take up to 130 microseconds to run. And this is the priority that it runs at, the priority order that it runs at. So we can go and have a look at the actual tasks running on this vehicle right now. And we can see the minimum time that each task took, the maximum time in microseconds, the average time that task took in microseconds, the total percentage of CPU being used for that task. So this is how you work out, how much of the time. You'll notice that this one here, 60% of our CPU, 64% is being spent on this read AHRS. And that is the EKF. That's our state estimator. So state estimation is the elephant in the room in CPU usage. It uses most of the CPU. In fact, that'll actually increase as soon as it gets a couple of meters off the ground. Why do you think CPU increases when you're more than 2 meters off the ground?
Because the EKF gets worse data.
It's not worse data. It's a really interesting one. And I didn't expect you to really know the answer. It's quite a tricky one. It gets, it uses the compass. The most expensive CPU operation that the EKF does is what's called compass fusion. Basically, compasses are really tricky to properly integrate into an EKF with all the different errors they have in it. They're very noisy, horrible sensors, but they're very useful sensors. And the problem is when you're very close to the ground or even sitting on the ground, you've got metal in among the ground. And so the compass is almost useless. So it uses a different fusion technique for the compass when it's on the ground, what's called a two-axis fusion or like a 2D projection, which is a much, much simpler fusion process and more like what you might do holding a compass in your hand, right? That's sort of a simple way of getting yaw. And once it gets more than 2 meters off the ground, it switches to what's called 3-axis 3D fusion, which is really CPU intensive, but much more accurate because it's expecting less error in the data from the metal in the ground. And when it does that, the CPU usage for Compass Fusion rises a lot. And so you're actually going to go up to sort of 70 or 80% of our CPU being the EKF. Yeah, compasses are very expensive. So there's lots of other, updates here. You can see things like, the fence check is taking, 0.0% of the CPU. There's a lot of tiny tasks here that use very, very little CPU. Then there's some tasks that use a bit more. So this is how you poke about with what ArduPilot's doing under the hood in order to see, how it's going there. We can also do things like get, I don't know, the memory, and we can see that. So this H7 has actually got a few banks of memory, total of 1 meg of RAM, but it's broken into a whole bunch of separate chunks. If I have a look at your logs, back to the log that we had from you guys before here somewhere. So Mav Explorer, this guy, we can actually look on your log. If I do file, right? So I can look, it logs a lot of these sys things in your ones as well. So I can do file sysmemory.txt, and we can see that on your quads, you have 192K of RAM broken into 2 segments, one 128 and 164K. We can also have a look at things like the threads
Andrew,
on your one. Yep.
I'm not seeing your screen right now. I think.
Oh, I'm not. Am I not sharing? I'll stop sharing and share again because it says I'm sharing, but let me share it again.
I saw it.
Yeah, we
All right.
can see it.
All right. How's that? You got it now?
Yeah. Sorry.
Yeah, no worries. So what we're seeing here is these are the threads that we're running on your little F405. A lot less threads because there's a lot less going on in your little vehicles. You're not doing, networking and PPP and drone CAN and those sort of things. So it's a much simpler vehicle with a simpler set of threads. But back to the question as to why we do thread per bus, it's basically because buses involve blocking. Right? So if you want to read from a UART, that involves waiting for a piece of hardware. It might take microseconds to milliseconds for that to happen. And if we were waiting around for a piece of hardware to respond and we were in the main thread, then while we're doing that, we wouldn't be trying to fly the vehicle. So what we do is we assign a thread to each of the hardware elements on your vehicle that could block. And they're basically all the buses. So we have a thread for anything that might, have to wait, wait for a response from an IMU, wait for a response from a UART, and then those threads do the waiting for you, and meanwhile, the vehicle can keep flying. And this is one of the reasons why ArduPilot is able to produce quite smooth flight, basically relying on what's called the RTOS, real-time operating system, and we run an RTOS called Chibios to do all of the very rapid thread switching between these different threads. Does that make sense at all? Yep. Okay. All right. Okay. So I just wanted to whet your appetite a little bit. You can get at this information using Mission Planner as well. If I jump into Mission Planner here and I have a look, I'm connected to the vehicle. You can go into config mav FTP. You can get these various files off your vehicle using Mission Planner as well by downloading it here down to some file. And you can then look at those files and view them in Mission Planner. Not quite as convenient as it is in Mav Proxy, but you can get the information from Mission Planner as well, from this sys interface. All right. So I might change tack a little bit. I was already open class, general questions, but if you're still sticking around for a few minutes, I'll show you some other interesting vehicles. So I might show you this little one. Actually, I'll show you a little tiny quadcopter. I've got one here. This is one of the smallest vehicles that ArduPilot runs. Very, very small little quadcopter, very, very cheap. It runs an ESP32 microcontroller and 4 tiny little propellers. I will warn you that these propellers suck up dog hair very easily. And so removing the dog hair in my house is a regular occurrence. But they're very nice little ones to play with, ESP32. Unfortunately, the CPU on it is very, very slow, very poor scheduling on this CPU. And it runs an operating system called FreeRTOS, and the scheduling is quite poor. It does mean that the flight performance isn't as good as your copters, but it can be fun to play with. Very, very lightweight little vehicle. There's a nice video from one of the ArduPilot developer conferences on how to play with these things if you want to. It runs this little tiny 1S battery. That's the battery for it, a little tiny battery. All right, so I was going to show you another little vehicle. So this is a variable pitch quadcopter. So this is a quadcopter, but you'll notice that it's got this belt drive, a single motor, right? Single electric motor up here. There it is. And that single electric motor drives a belt, which then drives all of the propellers at the same RPM. And then what it does is it has little servos that adjust the tilt of the angle, the pitch of each of these propellers, right? So instead of changing the RPM, it changes the pitch of the propellers, right? What do you think the advantage of that is?
It's lighter. Different stages of flight.
I'm sorry?
It's lighter because you only need one big motor instead of 4.
Yeah, it can be lighter, although generally it's actually used for very large vehicles. It's because the mechanisms, the servos are quite bulky, and it's quite bulky, the sort of those mechanisms. One of the main advantages is it scales better to very large vehicles. And so I wanted to show you briefly, so going from that tiny little vehicle I showed you, I'm now going to show you a fun vehicle that is you might like to have a look at. And so this is the world's biggest quadcopter running ArduPilot. And this one came directly, so it can lift hundreds of kilograms, like half a ton sort of thing. And here it is lifting a Bambi bucket for firefighting. But, that's just ArduPilot running inside there, and it's used for firefighting in Canada, and it's used also for things like, lifting huge things up onto the enormous, what are they called? Wind turbines. There's a nice video of it lifting something up for placing on a wind turbine. So really, really heavy lift vehicle. But the story behind this is quite funny. So I saw one of these variable pitch quadcopters on YouTube and thought, oh, that looks like fun to add support for variable pitch quadcopters. So I bought this dirt cheap off Hobby King, like $150 one that you can see there. And then I added support for that, these variable pitch ones. And they're quite nice in that they can fly upside down. Because they're variable pitch, you can go to negative pitch. You can actually do aerobatics on it where you fly it upside down if you want to. So it's a lot more aerobatic than a normal quadcopter. So added support for inverted flight with those, and can be very, very responsive. Because changes of pitch can be more rapid than changes of throttle on an ESC. Anyway, so then this company in Sweden saw that we'd added support for that, and they decided to build their first quadcopter. This was their first ever design of quadcopter. And they built this from that design. And then they contacted me and they said, oh, we're having some trouble tuning it. I thought, oh, sure, I can help you with tuning. I assumed it was going to be like the size of that little one. And then they sent me a video and it was the size of a truck. So they said, yeah, I'm not surprised that you're having a little bit of tuning issues, given the tuning guide that I did for this, 1.5 kilo vehicle. Yeah, anyway, it was a fun story. We've had a few things like that where people have gone to extreme lengths with huge vehicles. We're getting vehicles now, you've probably got like 3 or 4S. Oh, you're 2S, aren't you? So 8-volt vehicles. So what's called 2S. And some vehicles now, battery powered vehicles running ArduPilot, they're 100S. So 400-volt ESCs. So they're these enormous, and the battery packs for these things, you might have, 100, 150 kilograms of battery. on this thing, enormous batteries on these things. So it's been really fun that ArduPilot's sort of scaled up to these enormous sizes. And you probably heard about this Silent Arrow project I'm working on. I think Peter's told you about, there's some openings there available if you guys want to work on that, which is, that's a 2,000 pound, single use folding wing glider. Really fun project. And that's happening in Orange County, just around the corner from you guys. Anyway, I just wanted to show you that. I think it's quite fun, the range of different vehicles that ArduPilot runs on. So that's called the Thunder Wasp. So search for Thunder Wasp if you want more videos of that fun vehicle. So we're way over time here. And so did you guys want to have sort of any general discussion, questions or anything? I can stay for ages if you guys want to, but you guys probably want to get home and have dinner and that sort of thing. So what do you want to chat about?
I wanted to ask real quick, in the video you just showed, right? It was running ArduPilot.
Yeah.
And it was holding the payload at it was like dangling from it. So is there special logic in ArduPilot to handle that? Or was it just the vehicle was large enough so it wasn't that big of a problem for that swaying mass at the bottom?
Right. So there is special code in ArduPilot for that. I don't think that particular video was running the special code. I think it was just moving slowly. Right. And there was actually a funny video I got from somebody in China where they had put an enormous helicopter. And this was probably I think it was like a 600 or 700 kilo dual blade Chinook style helicopter. And they hadn't contacted us. It is a big thing, right? It was radio controlled, a big helicopter. It was probably worth, I don't know, $250,000 or something like that. Anyway, this helicopter, they hadn't contacted anyone on the dev team about tuning it. They'd just gone and tuned it themselves and flown it. And they had this enormous swinging payload beneath it. And it was then flying it along at quite high speed. And the payload started getting an oscillation, right? And while it was oscillating, the helicopter, ArduPilot, was in a position hold mode. I think it was just flying in loiter. And ArduPilot hadn't been told there was this payload beneath it. So ArduPilot was trying to counteract, right, the oscillation. So every time the payload swung this way and that dragged the vehicle right this way, ArduPilot would try to move this way to try to drag it back, and that would just cause it to swing back. And that caused the oscillations to get bigger and bigger and bigger, and eventually got to the point that this enormous payload, the payload was hundreds of kilos, on this long line, swinging more and more and more. And eventually the payload swung right the way over the top, wrapped around the top of this helicopter and completely destroyed it, right? And then they sent us the video and said, what did we do wrong? Right. And the first mistake was they contacted us after doing the test flight, right? I do have the video there. I'm not going to show it right now because I'm not sure if it shows the company at all. Don't want to embarrass them, but it's spectacular. Anyway, so of course, if they'd just switched to a non-position hold mode, it's just some pilot training. If they'd known they switched to alt hold mode, it would have settled down, right? Because it no longer had the feedback. What you've got is this sort of phase lag in the control, and that caused it to build up an oscillation. Okay. So that's basically a sort of a limit cycle oscillation being caused by this feedback from the position controller. Anyway, so one solution is just fly slowly, and then if it goes wrong, switch to a non-position hold mode like alt hold. Easy, problem solved, right? But if you actually want to do it properly, then yes, you do actually want to have special control for slung payloads. And so let me have a look for a video, Randy Payload Place Conference ArduPilot. So let me see if I can find the video of this position offsets, the 2024 conference. It's on YouTube. So Randy did a lovely demo of this 2024 ArduPilot conference. And there it is, 2024. If I find the list of videos, then let me see if I can find the full playlist, right? And Randy McKay's one here. Oh, I should have had this pre-prepared. There's the welcome from Randy, but there's a lovely video where he demonstrates doing beautiful, I think it's the position offsets one. And let me just seek forward to this where it's doing payload place test, where it's got this quadcopter with this slung payload, and it's placing this slung payload at a precise position on the ground. And the way they do it is he actually put a second flight controller on the payload, and then that's transmitting up via Bluetooth to the vehicle up the top here, right? And then it then uses that to calculate the corrections it needs to do in position in order to place the payload at a precise position on the ground where you want it, and works beautifully.
We can't see the screen.
Oh, you can't see the screen. Oh, I'm not sharing now. I'm an idiot. Yeah, there you go. Okay, meeting, screen share. You've got to jump on me quicker than that when I forget to. There you go. So here is the slung payload. So you just sort of search for Randy, ArduPilot, Dev Conference 2024 position offset. And so this is where you can see the copter there and the slung payload beneath it swinging about, and he turns on the control of that and it stops swinging about as it controls the payload precisely, and then it goes and lands. In this case, the demo, it landed within a couple of centimeters of the desired position. Which was really amazingly accurate for such a long cable. It was like a 30 or 40 meter cable below, and it lands really precisely. Let me see whether I can find Leonard Hall dual payload lift. So variants of this. So there's a nice example of I don't know where the video is. So search on YouTube for free space. Come on, why is that gone to space dual lift? Hopefully finds that cooperative lift system. So this is an example where you've actually got two quadcopters, two big 50 kilogram capable quadcopters, and they lift off together, and then they have the payload slung between them. Right, so if we go up to here, you might be able to see, there it is. Can you see there? There's the two quadcopters flying with the payload slung between them, and it's controlling the position of the payload precisely using a dual lift system, which is really nice. So ArduPilot has a lot of this stuff. So it can do precise control of slung payloads and even cooperative lift between vehicles. And that requires very precise control. These are very expensive vehicles, so you really don't want them to run into each other. And so it can basically lift them and control the position of that swung payload beneath. Does that answer your question?
Oh yeah, absolutely.
Yeah. So it's a lot of fun, this stuff. The testing is a lot of fun. The test pilots have got to be really on the ball when they're doing this, because things don't necessarily work perfectly the first time. So, simulation's good for that. All right. So, any other questions? I see there's a whole lot of things been going on in the chat here, which I've completely ignored. So, if there's any questions you've got, feel free to ask now.
I have a question.
Yep. Peter.
These are 21-year-old, on average, students just entering their career.
Mm-hmm.
Some of them are going to be in tech. Some may leave tech. I don't think the drone industry at this point is going to hire all of them, although
it might.
It may, because the industry is growing so exponentially. But what advice would you give them as they enter their career?
Right. Well, getting involved in open source projects can be really, really good, because it allows you to demonstrate your expertise You can build up a portfolio of what you've worked on without having to work for the company first, because it's always the trap of, they want to hire somebody experienced. How do you get the experience? You've got to be hired, right? But working on open source projects, there's a very low barrier to entry to get in there. So you basically have to dive in and geek out on these projects. Turn up to the weekly dev calls, jump in the Discord, get involved, start making modifications to the project to learn how to do things. If you can, get into Google Summer of Code. Have you guys, does UCIrvine do GSOC?
I haven't heard of it. No, maybe not.
Look up Google Summer of Code. Really worth getting involved in that. Basically, you get mentored. There's thousands and thousands of free software projects, open source projects that propose projects for the summer. And any student around the world can apply, and you've got to put a lot of effort into your application. If you get accepted, then you will be mentored by one of the experts in the field. Randy or myself or Leonard or someone else in the project might mentor you for a few weeks to months. You're paid during that period. Google pays you to work on the project. And the aim is for you to actually make a contribution to the project over that period. A lot of the lead developers of ArduPilot originally joined the ArduPilot project through GSOC, right? So they basically, if you look at the people who are right now have full-time, really well-paid jobs doing ArduPilot, a lot of them initially were students like you who joined up through GSOC, were mentored by people like myself or Randy or others. They got to know how to make change to the code. They worked on a project within the ArduPilot project and got their code, reviewed and included included in the next release. And then you start to find that people start, making job offers, right? You then start finding that, if you're good, people will notice, and you can start doing some consulting around ArduPilot, turn up to conferences, get involved. That is one of the things, but you have to be passionate about it. You have to, put time and effort in to learn about it. It's a big code base. It's including the RTOS and things. It's well over 1 million lines of code. You don't have to understand all of it. You can, specialize in a particular niche area. You've got to learn how to build and run simulators. You've got to learn how to, how to use GitHub, how to do code review, that sort of thing. But yeah, there's a lot of opportunities if you get involved. We're often asked, where can companies hire someone who has expertise in ArduPilot or other open source projects? ArduPilot might not be your passion. Look at the list of GSOC projects. The next time GSOC comes up over your summer, and it's a huge list, absolutely huge. So, yeah, really get involved. All right.
And then slightly more technical question, I guess. What was, if you're aware, but what was the guiding decision, or not guiding decision, ArduPilot's PID based, like there's a lot of nested PIDs, but then there's also controller types, which are like recently for another competition where we had more control over the vehicle. I wrote a geometric controller, for instance, for that situation. And then there's also a ton, like there's an indie controller, and there's a lot of different control techniques. But is there a reason why ArduPilot likes to stay with the nested PIDs besides the generality, I guess, of it, and it doesn't have like these other controllers within it?
We do play with a lot of other controllers. You'll find there are open pull requests for all sorts of other different controllers. There's neural network based controllers, and there's other sort of optimal control techniques, and there's lots of different ones, right? Controllers that we dabble with, right? But we're looking for controllers in academia. Very often they work well for the paper, but they don't necessarily generalize and have the robustness that we need. getting a controller to the point that it's robust enough to be used across the range of vehicles. You've seen the range of vehicles ArduPilot's used, and we've only just touched the surface in the range of vehicles, right? There's a lot of other different sort of vehicles ArduPilot's used for. The nested pit approach can be very, very robust and very easy to understand and to analyze. But we do have other control techniques, like we use an L1 controller for lateral navigation in, fixed wing. We use other types of, controllers in other parts of the code. So there's like an S-curve controller that's used in multi-rotor waypoint navigation. So you were using an S-curve controller almost certainly when you were doing that waypoint navigation for your one. So there are other controllers we use and we dabble with them. If you've got a particular type of controller you like, try it, implement it, give it a go, get it working well in simulation, then try it on some vehicles. But when it has to be really generalized. We actually have a controller framework where you can have multiple controllers running simultaneously and switch between the controllers with an RC switch. And that's how we've evaluated people's new control schemes. So when somebody comes up with some new fancy control scheme, they implement it using one of these, secondary controller schemes, and you can actually be flying the vehicle and flick between the controllers while you're flying it. And so you can get a really good idea of how well it works. We've also got, you can also, throw in a MATLAB controller and actually feed MATLAB into ArduPilot if you want to. And people have done that to try out new controllers with MATLAB if they feel like doing it. I don't like MATLAB myself, but, we support that as an option. So there are a lot of options, but it's really robustness because ArduPilot tries to be a very, very robust system. A lot of these controllers tend to work extremely well under a narrow set of circumstances. And then some of them that work well under a broad range are just more difficult to tune. So a lot of the ones that are supposed to be sort of self-tuning, you have to end up with 50 parameters to control the self-tuning, which means you've got as many parameters there as you had when, you just use PIDs. So look, if you've got one, a favorite one, try it, implement it, play with it. You'll learn a lot, regardless of whether it works out. And who knows, you might be the one that, brings that controller into ArduPilot. Stranger things have happened. Students, all of the current developers in ArduPilot started off as students somewhere, right? So it happens. But it's as ArduPilot gets more and more professional, the barrier to entry of bringing in a replacement for our control scheme gets higher and higher. So it gets harder to do that.
Yeah.
I had a question about fixed-wing VTOLs.
About which one? VTOLs?
Fixed-wing VTOLs.
Sure.
So I just started working on a company 2 months ago where that's like their main commercial product they sell.
Right.
And the drone pilots there, they have a problem doing a smooth transition from horizontal to vertical and vice versa. And I was wondering if there's any tips or advice you have to get that transition smoother.
Sure. Well, there's lots of sort of tuning tips that are up on our wiki. So ardupilot.org, we have lots of documentation and things. The first trick is to think about the layering and the controls. So make sure your rate controller is really good. Before you get your rate controller good, make sure you've got your notch filtering really good. So, ESC, RPM feedback, that sort of thing. Make sure your state estimation is really good because it's not going to get good control without good state estimation. So work from the bottom up and make sure all of those layers are good before you get up to the level of the velocity control and the transition control, etc. So if they're just wanting professional support, they can join as an ArduPilot partner company and get logs reviewed professionally. If they're happy for the logs to be public, then you could ask someone like myself or one of the other dev team members to review the logs publicly. A lot of companies would prefer their logs be kept private, in which case that's why we have this commercial option where they can be a partner company and they can then get, commercial support and log analysis, log reviews. Because there's ArduPilot on that sort of vehicle probably has around 2,000 parameters, and there's a lot of things you've got to get right in order for it to get a really smooth transition. And so from your description, I can't immediately work out the issue. There are a lot of complex aerodynamics going on with forward and back transitions is it an SLT or is it a tilt? So is it separate lift and thrust, or is it tilting the motors?
It's tilting the motors.
Tilting the motors, and
sorry, no, separate. When you mean separate lift and thrust, there's forward motors and there's vertical lift motors.
Okay, so separate motors. So that's called SLT, separate lift and thrust. Yes. And are the forward thrust motors, are they internal combustion engines or are they electric?
They're electric.
Right. Okay. And do they have RPM feedback on those motors?
I could not tell you.
Right. Very worthwhile having RPM feedback if you can.
Okay.
And that makes it much easier to do the analysis, and much better filtering, much lower noise as a result, like I showed you earlier with the harmonic notch filtering. So then there's a whole bunch of parameters regarding your transition. You've got to do good velocity tuning and position tuning, and there's also things regarding the drag of the aircraft. So ArduPilot takes advantage of the natural drag of these sort of aircraft. Is most of the issues in the back transition when going from forward flight to vertical flight, or forward transition from forward flight to from a hover to forward flight?
I'm not entirely sure. I know we have issues with both. I was just looking for general tips. I'm sorry I can't give you very in-depth advice.
That's all right. Yeah, that's all right. So look, if they wanted to share a log with me, we could have a bit of a peek at it together, and see if we could work out why. It's a bit hard from your description. I'd need more details to really know what it was like. A detailed flight log along with a video as well can be useful. And then I could sort of offer some more advice on how you might tune the vehicle. It does take quite a while to get a really good tune. Getting it flying sort of acceptably is reasonably quick, but getting it a really good tune does take some effort. And a lot of people skip steps in the tuning process. We have a sort of a detailed set of tuning steps on our website, and most companies skip at least half the steps. And a lot of it's about telling people, go back and complete step 2 that you skipped. And I can tell you skipped it because the values are at the defaults, and there's no way that your vehicle should be having the default values. So I'd really need those details. Look at the logs, and I can see which steps have been skipped, and then hopefully offer some more coherent advice.
Yeah, that makes sense. Thank you.
Yeah, no worries at all. Yep. All right. So we're now half an hour over time. I'm very happy to keep going if you guys want to. I can jump into other things. I was going to, fly the simulator. You guys seen the real flight simulator, flying that? I was going to give you a quick demo of that if you wanted to see it, which is quite nice. That can be, if you want sort of a visualization. I'll go and share my screen again. Let me see. There it is. And now somewhere here, I had a terminal. And somewhere here I was running this one here. So what I'm going to do is, let's see, Mav proxy that console. So what I've got is a VTOL fixed wing, a tilt VTOL fixed wing here, and which I'm running in something called Real Flight, which is a simulator. So I've got, I don't know whether you can see my video at the same time. There's a transmitter that I'm holding, and I can, fly it around here like this, tilt it. This is a tilt quad plane. This is a model of something called a Griffin Pro, and I can fly it around here, or I could just switch it to full auto mode to do a full auto mission. So I'll do that now. So I'll just say go to auto mode. So it's now going to take off in auto mode and run a full mission. And so that's it running a little mission there. It's going to take off to maybe 40 meters and then transition to forward flight and then fly back. And then I'll tell it to go in and land. And so there it is going to forward flight. And I don't know whether you can see that very well. I might need to zoom in on that, manual zoom, and then zoom in. You might be able to see it a little bit better. So I'm going to tell it to come in and land. Anyway, it's quite fun playing with this. You can also edit the physics in these vehicles and, play with the vehicle somewhat. Lots of different types of simulators you can use with ArduPilot. So, yeah, anyway, worth playing with those things if you've got them available. All right. So what other questions do you guys have, or should we finish off there? No? No more questions?
Well, I mean, Professor Burke, how long are you comfortable with this running?
As long as I'm fine, as long as you guys want. Be respectful of Tridge's time.
Yeah, I'm fine with it. If you want to chat a bit longer about different things, you could tell me more about the projects you're working on.
Yeah.
And
if you do post this on your YouTube channel or any other venue, please let me know, because the other students that couldn't come probably would be very interested. And honestly, the whole world, because you've given a lot of interesting advice about a lot of different topics. So just let us know. But yeah, these students probably have a lot of questions, so I'm happy to have. I'm learning a lot myself, so I can stay all night. But whenever Tridge wants to call it off, because he has other obligations as well, and he's doing this out of the kindness of his heart. So we should really thank him.
Oh, I enjoy it. It's good fun. All right. So you got a slightly bigger vehicle there. That's not the vehicle you were using for the little logs that I got, I'm guessing. Yeah. It looks like a bit more battery on that one, a little bit larger. And so tell me about this one.
This is Weaver. It's, how big is it?
It's a 15-inch. I don't know how much the wheelbase is, but it's approximately 7 kilograms.
Yep. Okay.
Yeah. And for thrust, we have 465 kV motors for them at running at 6S, and we have an 800-watt battery. That's made up of a bunch of parallel groups. I think hover throttle, in terms of flight characteristics, hover throttle's around 52%.
Or no, not
right.
Like,
okay.
We have a 2-to-1 thrust.
Yeah. 2-to-1 thrust to weight, right?
Yep.
Yeah.
Okay.
So a very interesting thing about this implementation is that we had to, I think we ended up not using a current sensor, voltage sensor for the battery. So for the longest time, we were flying blind, basically. Like we had no current or voltage readings streaming into the flight controller. Yutaro here, he ended up implementing a sort of a voltage readout through a ESP32. We have a current and voltage sensor on that.
We have a separate PCB board that contains the current and voltage sensor, which does the current and voltage readings. But I guess we were having a fun time.
So there's a NVIDIA Jetson on here. It's the onboard computer that runs all of like the flight scripts through PyMavLink. It's just a serial connection.
Yep.
And the Jetson communicates with the ESP to get the latest voltage and current readouts. And what we were wondering is, or what we're trying to implement now, is how can we forward those voltage and current readouts to the flight controller through that MavLink connection? Because I'm not familiar with the way that's supported.
Okay, there's several different ways to do that. Well, first of all, just ask, what flight controller do you have on this?
We have the Holybro Pixox 6X.
6X.
So
Great. Okay. Nice. So it's one of these. If I just disconnect it from my, thing there. Yep. Nice flight controller. It's got built-in Ethernet, which is very nice. So you can put the Ethernet from that straight across to your NVIDIA rather than using a UART, which is very handy. And also great for Ethernet for all sorts of other bits and pieces. What ESCs do you have on here?
I think we have a T-Motor 4-in-1.
Yeah, 80 amp.
80 amp.
D-Shot right now, D-Shot 600.
Right. So it's a T-Motor is 4-in-1. Is that the AM32 or the BL-Heli 32 version of it?
Should be the AM32 version. It's the new one, I think.
Right. So that means it's almost certainly capable of BD shot. In fact, it'll support the extended BD shot with telemetry feedback, which means you could get voltage and current from the individual ESCs if you want to.
We tried that, I believe, but I think we ran into some issues with that. Earlier, we were also using on another one of our quads. Are you familiar with APD? Advanced power. Yeah,
yes.
So we were using
now known as Hargrave. They've rebranded as Hargrave. Yep.
Yep. So this was we made a X-class racing drone. Our first.
Nice. All the APD ESCs are capable of the bidirectional D shot. So you should be able to get telemetry back from it, or at least RPM telemetry, if not the full extended telemetry, where you get voltage and current coming back. So that would be my first way I'd look at getting the voltage and current in. But if you want to play around with getting telemetry from an ESP32 into ArduPilot, the first thing I'd reach for is Lua scripting. So on this, the ESP32, how does it physically attach to the NVIDIA? Is that like a UART?
It's the UART, yeah.
It's a UART. Okay, great. So you've got a UART, and you've made up your own little UART protocol for that?
Yep.
Yeah. Okay.
Yeah.
Well, I would consider attaching it instead of to the attaching that to the NVIDIA. You attach it to a UART on the Pixhawk 6X. It's got heaps of UARTs, and then use a Lua script to parse that protocol, and then you create a battery monitor in Lua. So do you know what Lua scripting is?
Not enough, I think. I think
Okay.
it would be nice
So
to hear more.
Lua scripting is extreme. You've almost certainly used Lua scripts without knowing it. Lua scripting is very, very widespread in the electronics industry. So lots and lots of things, household items and other things have Lua built in. Lua is a scripting language, embeddable scripting language with wonderful interfaces into C or C++ code. So if you've got, like a transmitter, like something like this type of transmitter, right, it has Lua scripting built into it. And a lot of the display and things is done using Lua. So ArduPilot has a very nice Lua interpreter built in with lots and lots of bindings into ArduPilot. By bindings, I mean there are function calls you can call in Lua that access the internals of ArduPilot. There are, many, many hundreds of APIs that you can call. And you can run Lua scripts at very high rates. So if you want to see what Lua can do, have a look for the aerobatics scripting that I did for a conference a couple of years back, where I had a Lua script that took over all of the control on a fixed-wing aircraft and makes it do full aerobatic schedules, Immelman turns, loops, split S's, an entire air show completely using a Lua script, and flies it as well as sort of world champion pilots. So really, really precise control. Anyway, so that's what you can do in a Lua script. So you can do, Lua scripts are commonly used for device drivers, and that's what you've got here. You would need a device driver to create a battery monitor in Lua. And that battery monitor can be as simple or as complex as you like it to be. And that little Lua script will read from the UART and then will create a battery monitor, and then it'll appear as another battery monitor on your vehicle. And then you've got voltage and current. Now, you could do the same thing with the NVIDIA. If you've already got it going into the NVIDIA, you could make the NVIDIA squirt it at the ArduPilot flight controller, the Pixhawk 6X flight controller over, for example, TCP/IP. You could send the battery updates as, say, UDP packets, right? And get a Lua script to receive those UDP packets, and again, create a battery monitor from UDP packets. So the ESP32 would be generating the voltage current data, going over a UART to the NVIDIA squirting it as UDP packets across to the flight controller, Lua script on the flight controller, listening on that UDP port, parsing those UDP packets. It could be something like JSON packets if you want it to be nice and structured, or it could be a proprietary binary format. There's a JSON parser built into ArduPilot you could use. It's actually a Lua module in ArduPilot to do JSON parsing.
So right now, we primarily use Mavlink for our communication between the Jetson and the Pixhawk, right?
Yep.
What you're suggesting, the way I'm interpreting it as we can either just use an existing Mavlink message and then write a custom Lua script in the ArduPilot firmware or whatever, and use that to somehow inject it, or is there a already existing method that could make this work, like having the Jetson update battery status within ArduPilot itself?
So there isn't currently, as far as I'm just looking through the list of battery monitors that we've got, I don't think we've got a bat monitor scripting for creating a bat monitor using Lua scripts. I don't think we've got a bat monitor Mavlink for doing Mavlink. We could easily create one of those. But at the moment, if we look at the list of battery monitors, this is the source code for AP Batmon in ArduPilot. I think it would be most easily done using the Batmon scripting. This is the back end for creating a battery monitor using a Lua script, and make the Lua script either read the UART directly or receive the data from the NVIDIA board. Now, you could make the Lua script receive Mavlink message, and then it could parse the Mavlink messages and then create the battery monitor that way. It's a bit indirect, but you could do it. But I would probably either make it go direct from the UART into the script, or I'd go via, say, UDP packets from the NVIDIA into a Lua script. But first of all, check if your ESCs can do it directly. So you can get voltage and current from the ESCs directly, because that's by far and away the easiest thing to do. And that would also give you the RPM feedback.
Yeah.
If we choose to go through the ESC for this, we won't be able to see like auxiliary power draw from like other devices, right?
That's correct. It'll only get the current that's flowing through the ESCs, which will probably be the majority of your current, right? But yes, it would. It's not going to see. You get the overall voltage levels. So you can see when your battery is becoming depleted. But particularly if you turn on the option in the battery monitoring for ArduPilot to estimate the resting voltage of the battery, where it removes the impact of the drawdown from the current by it has a little estimator for the internal resistance of the batteries. And just uses V equals IR to estimate the resting voltage, and that allows you to know how close you are to running out of the battery. So you can certainly do that, but it's sort of up to you guys, how you do that. How sophisticated you want to get, but if you want to cover all of the current going through it, you obviously got to measure it at the battery level.
And then this is a more dynamics question, and I couldn't find a quick explanation for this, but like in a quad plane state, right? When you're transitioning from a fixed wing to your quad state, and in the simulation also what's documented is what it does, the plane will go into like a stall and then let the quad motors take over. And
it tries not to actually stall it like that, but
sorry, what did you say real quick?
It tries not to stall. So the back transition process is more, the first step it does is it fires up the VTOL motors just to add drag, like throwing out a boat anchor. And it relies, it's what we call, in the forward transition case, transition drag. In the back transition, it uses what's called the momentum drag of the propellers. So if you drag a propeller sideways through the air, right, then the thrust of the propeller produces momentum drag, which is actually quite draggy. So what we do is, as we're coming in for the landing, we actually fire up the VTOL motors, not to give lift, but just to give drag in what we call air braking. And so that slows down the vehicle without the vehicle having to climb. Because if you just pitch up, then if you're flying at 100 kilometers an hour and you pitch up in order to get, the thrust going backwards, the thrust vector going backwards, then you're going to climb like crazy, right? So instead, we try to keep the vehicle fairly level, and we turn on the VTOL motors at a fairly low throttle. And what that does is creates drag using the momentum drag at the propellers, which slows the vehicle down, right? And ideally, it never has to pitch up at all. And then we slowly raise the throttle, so it's transitioning from being on the wing to being on the propellers, slowly, smoothly, and coming to a perfect stop above where you want to be, right? And then descend. That's the idea.
So that's what I was looking towards. But in sim, we've tested 2 VTOLs in sim right now, the Alti transition quad, and then also the Skywalker X8, and both of them exhibit the pitch behavior I was mentioning, where it goes and then it pitches up and then it comes into like a quad state. I'm wondering, can that be tuned out then? Is just the
you can tune it out. In particular, you want to change the back transition drag parameter, and it's called a deceleration parameter, which isn't actually a very good physics model it's using there. It's quite poor, but it works. I should say though, if you're using the LT, you're probably doing this in something like real flight, and real flight has very poor simulation of momentum drag. Which means that the vehicle doesn't slow down with the air braking as much as a real vehicle does. And which means it's actually harder to get that perfect back transition with in real flight than it is on real vehicles. But just because the physics simulation it does just doesn't simulate that momentum drag particularly well. It does a little bit, but not really properly.
We're using Gazebo for that. How much of a difference?
I don't know. You'd have to look in the Gazebo model and see whether it implements momentum drag. A lot of them just implement single axis, so they just basically model the motor as producing thrust, right? And they might model it as producing drag in the forward direction. If you run the propeller slowly, more slowly than the airspeed, then they might model that it produces some drag there. But it's a more sophisticated model to measure the drag when the propeller's going sideways through the air. And that's what you rely on for a good back transition. So yeah, the models tend to be not very good.
So then in the best way of going at this design would just be empirical testing at that point.
So empirical testing, you can lower this transition drag parameter, and so basically say that it doesn't have as much drag, and which means it'll start the transition early. A really common mistake that people make with these sort of vehicles is they try to land in too short a distance. These vehicles, they're quite big vehicles. Like the LT transition, it's 3.2 meter or something of that order wingspan. It's quite a big vehicle, right? If you see it in real life, it's big. And when it's doing its back transition, a lot of people set it up so it only has 50 or 100 meters to land in. And it just can't slow down using its natural drag and the momentum drag in that time, right? So what you need to do is, first of all, set up the mission profile so that it already is slowing down before it even starts the back transition. So you actually have, as part of the mission, a change airspeed command to say, slow down and get, minimum speed on the approach. The next thing you want to do is you need a nice long distance. If when you start it puts out these little messages, right, where it says, air braking stage, and then after air braking, it goes to position 1 stage, position 2, and then it goes to, land descend, and then final descend, etc. All these stages. If you're finding in your landing that it's skipping the air braking, or the air braking is only going for 1 second, right, and then it's into the position 1 stage, that means you didn't give it enough distance to land in, right? Because it didn't give it a chance for the air braking to work. And you want 10, 15 seconds worth of air braking. Now, the Alti flies at what was it, 23, 24 meters a second? So 10 seconds, you're talking a couple of 100 meters. You want just for the air braking, right? So you need to really give it that time to slow down and do an elegant. It means it's running the propellers for longer, but it actually uses less battery because it doesn't climb as much. And most of the battery is using in the descent stage when it's a pure quad and it's not on the wing. The battery consumption during the air braking phase is minuscule. So you actually get a much more elegant landing. But a lot of people assume you want a fairly short landing, and they just don't set the mission up to have enough room to land.
So then how much of this can we do without it being in, because right now I see all for the VTOL, because for preface, when we're using the quad last year, we didn't do any like guided like waypoint type missions. We used direct set points, the set point Mavlin command, where we're able to direct the velocity vectors directly, or like heading.
I wouldn't use quad planes to fly VTOL waypoint missions. It's not designed for that, and they fly them horribly. So you basically tell it you want to land here, you want to take off there, then you start flying fixed wing. Quad planes are designed, or VTOL fixed wing in ArduPilot, they're designed for 30 seconds worth of takeoff, 6 hours of fixed wing, and then 30 seconds worth of landing. They're not really designed for doing hovering around doing stuff. That's not what it's for, and it does fairly badly at that.
So is that because right now that's part of our mission, like that's what we had planned, was that so our vehicle, for reference for our project, the mission or the competition we compete in, our goal is there's an endurance section, which is why we want the fixed wing portion of a quad plane, but then there's also ODLC, object detection and localization, and then we drop a payload on our detected object, whether it's like we're delivering water for search and rescue or something like that. So our idea was that it's in quad plane, it does endurance, and then it switches to it's in fixed wing mode, and then it switches to its quad state over the area, and then we do our scans while we're still in a quad state, and then we precisely go over to where we need to drop our payloads. It's not a large mission area to do that, but is that still something feasible we can do? Or
you can do that. So, okay. So first of all, have you seen the quad plane payload place Lua script?
No, we have not.
Okay, you want to have a look at that. So that's a Lua script that I wrote specifically for this type of thing, where it automates the process of placing a payload, lowering it, and you can either do it as it's like dropping a payload, or you can tell it to come in, back transition above the point, come down, land on the point, and release the payload, then automatically take off again and forward transition. That's all automated in that script. You could combine it with precision landing if you want to, with like markers or whatever. So you definitely should look at that Lua script. If you want to do when you say doing a scan, how big an area do you want to scan?
I need to interrupt for 1 second. I'm going to try to extend the zoom.
Right.
Because it had set to expire in 1 minute. So if it expires, we're done, I think. But let me see if I can extend it right now, okay?
All right.
Because computers have control.
Yeah, we actually also have a meeting at 7 right now.
All right. We should let you get to your meeting. You can always jump on Discord later and say hello, and ping me in the general Discord channel. But I am going away for a few days starting tomorrow morning, so you may not catch me for a few days.
No worries.
So I can't do it. So in a few seconds.
All right. Well, it's been great. Thank you so much for inviting me. It's been really fun, and happy flying.
All right. Thank you so much.
Thank you. Bye-bye.
Bye.
Bye.